Hello everyone, my name is Brandon, and today we're going to study some quantum mechanics. So first I just want to talk about my purpose here. I'm starting university in around 8 months. I just finished up my associate's degree in physics at a community college, but most colleges don't accept fall transfers. And I'm also doing this just because I love physics. Also, speaking of university, it's very expensive, so if you can support me on my Patreon, that'd be very much appreciated. Okay, now what's on today's agenda? We have the Schrodinger equation and the statistical interpretation of that and probability. Now, what are my prereqs for this? Well, I've taken Calc 1, 2, and 3, which is like multivariable differential and integral calculus. And then I've taken differential equations and linear algebra. And we're doing this out of the Griffiths textbooks, the 3rd edition. And also, this isn't just a basic study with me. I'm going to be sharing what I'm learning and try to explain it myself, kind of use that Feynman technique. So that being said, if you are a student who's also learning quantum mechanics, do not take my word for this, because I could be totally wrong, because I'm a student myself. And if you are someone that has experience in quantum mechanics and sees something I'm doing wrong, or if I'm not saying something correctly, I would really appreciate it if you left it in the comments. Okay, I am also neurodivergent, so I have OCD and ADHD. So I'm also going to be explaining different ways, different techniques that I'm trying to learn things, because the neurotypical ways of learning do not typically work well for me. So if you are also someone that's neurodivergent, maybe this is something you can also take away. Okay, now let's get to studying.
Yeah, so the way I'm going about this is that I'm literally just going straight through the textbook. I'm really trying to understand all of the derivations. So if it skips a step in a derivation, I'm going to be making sure to understand it fully and go through it from scratch, instead of just like being like, hey, oh, like here's the final product. No, I'm going to go through everything.
Okay, starting off here with 1.1, the Schrodinger equation. So the textbook first started off with talking about how in Newtonian mechanics, you can determine the position of a particle as a function of time. So x of t, take the derivative, you got velocity, and then from there, if you know the mass, you can find the momentum. In quantum mechanics, that's not necessarily the case. We'll get more into that later. But what I thought was interesting is that they define force as the negative del v divided by del x, and del V being the potential energy. And I've never seen force expressed like that, so I was interested in its derivation. Starting off here, we have work equals force times its displacement. Now, if we wanted to find an infinitesimal small amount of work done, it would be dW equals the force times dx. And we can reasonably say that dV, which is the potential energy, equals the negative dW. And this makes sense. I'm not necessarily sure if it's correct to think about it this way, but I'm thinking about it as a spring. So if I'm pushing on a spring and the spring wants to go the opposite way, I'm giving it more potential energy, because if I let go of that force, the spring is gonna wanna spring in the opposite direction. And then yeah, so I defined the signs right here. Positive, if I'm going with the spring direction and it's not past its equilibrium position, then yeah, it's definitely going down in potential energy. So since dV is equal to negative dW, we can just replace it. dV equals negative f of x times dx. And then from there, we can say f of x equals negative dV divided by dx. So that's where that derivation came from. I never thought about it that way, so that was interesting to see. Okay, what I like to do whenever I do a derivation, I like to practice it immediately after, just to make sure it sticks. So that's what that pink is right here. And then, of course, f equals ma, which is this yellow part, which can be expressed as d squared x divided by dt, set it equal to what we just derived. And then essentially what the textbook was trying to say here was that we can find x of t from here. Reason being that if we were, it's like a second order differential equation, I think. Okay, now we get to the cool stuff, which is the wave function, which is in blue here. Now I like to highlight whatever things that I think are like formulas or something that's really important. So, I'm not even going to try to describe this mess, because they kind of just brought it up and they didn't really go too in depth. But really what the wave function does, it's basically like finding x of t in Newtonian mechanics, but in quantum mechanics, it's like a probability that I'm going to find a particle here or there. Like you can't really know for sure type thing. So yeah, so it's like finding the position in classical, but with probability. Okay, 1.2, statistical interpretation directly related to the wave function we were just talking about right up here. So if we integrate from a to b, the absolute value of the wave function times dx, it's going to be equal to the probability of finding a particle between a and b at time t. So relating back to that probability right up here. So yeah, something really important to mention that is pretty cool to me is that quantum mechanics is inherently indeterminate and only offers statistical information about possible results. So what we got right here in this first graph from the textbook is the absolute value of the wave function squared as a function of x. So we get obviously an oscillatory nature here. And if we're looking at the amplitude of a here, the particle is most likely going to be found at a. But going back up to our integral here from a to b, that is what we are integrating over. So once we solve this, and whatever percentage we get, that's the percentage of the particle being between a and b here. Also, something that I also learned about that was pretty cool is that once we find the particle wherever it is, then the wave function collapses. So like this oscillatory mess up here just completely flattens out and maxes out wherever the particle was found. So from here, this first graph here, the particle was found at point C, and then if we were to measure it again really quickly, we would find it again at point C. Now, this is the electron interference pattern, so going through like a double slit or something like that. And so if we're going chronologically here, we're going from A to B to C to D. So as you can see, at A, we have these seemingly random particles, or the random positions of particles landing on the screen. And it's inherently just unpredictable. Like we'll find the overall pattern, but determining what the electron is going to do seems ridiculous to say if you weren't talking in terms of probabilities. So quite fascinating, really. Okay, moving on to 1.3 probability. I hate when you're like learning about really cool stuff, like for example, like quantum mechanics. We just saw those cool equations earlier, and then we kind of have to go back to basics. So this is like a basic statistics section, which I actually struggled the most with. So I guess I really needed this. But the textbook started off with giving an example of a group of people, all separate ages, what's going to be the probability of finding, if I were to pick one individual from the group, what's the chance of what age they'll be? Pretty straightforward. For example, there's only one 14-year-old person here, and what's the chance of finding them? Well, it's just 1 divided by 14, so it's pretty straightforward. So we can define the probability of j, which is the age, is equal to n of j divided by n. Also, one thing I wouldn't have put together intuitively, if we wanted to calculate the probability of getting age 14 or 15, it's actually the sum of the individual probabilities. And of course, this right here, the sum of all probabilities must be 1, and that makes sense because we have to, if we're going to grab an individual and determine their age from a certain group, there's a 100% chance that we will find someone, if that makes sense. It's almost too straightforward, it's confusing. Okay, and this was really funny right here because there were some exercises, and it said what was the median age. I totally forgot what median meant. I think that was like back in 4th grade. I'm also a non-traditional student. I'm 26 years old, so before I came back to college, I hadn't done math in like probably like 6 years or something like that. But median, pretty straightforward. It's just whatever's in the middle. And if it's not like a nice set of numbers and there's like no middle, you just take the first 2 and divide it by 2. So the median age here is just going to be 23. Okay, on to the average value or the mean of the ages. So I didn't write this part down, but if we were to find the mean of the ages, we're going to sum up all the ages plus how many people are that age divided by the total number of people, which is 14. So that would be like 294 divided by 14 equals 21. Another way to describe that is, it's funny, I read this as the inner product. That's probably not rigorous to say because I think it's being used in a different context here. I just got done with linear algebra, so I see this as the inner product of j is equal to the summation of j times n of j divided by n. Well, we know from earlier that n of j divided by n is equal to the probability. So we can just say j times p of j is the mean value of j. And kind of just making the same analogy here, we can also say that the quote-unquote inner product of f of j is equal to the summation of 0 to infinity of f of j times p of j. As you can see here, it's like low-key a function. That's kind of like the analogy that's getting me through this. It's low-key a function. Okay, so what we got here in this new graph is that they obviously look very different, but they're very similar in a lot of ways. They have the same average, the same median, and the same most probable values, and the same number of elements. So, one way we can determine the difference in these graphs is to find the spread within the distribution with respect to the average. And a way you can describe the spread in distribution is the change in age equals the age minus the average age. So that's finding how far each individual is from the average or the spread. And basically, we got a bunch of mumbo jumbo plugging in stuff. Essentially, what we're coming down to is that sigma squared is exactly equal to the average of the change in age squared. And this is also known as the variance of distribution. And then we have sigma alone just equaling the standard deviation. And then if we go through this theorem, I'm not going to go through it. You can pause if you want. It's kind of just simple algebra. But if we go through this theorem, we essentially get that sigma equals the square root of the average age squared minus, you know what? I might have that wrong, actually. So it's actually the squared's supposed to be on the j, and then this part's correct right here. So we got the standard deviation.
So, oh man, so I've been studying for probably like an hour and 45 minutes, and I'm tired. Usually I don't get tired this quickly, but maybe it's just because it's quantum mechanics, so it's a little bit more complicated than the lower div stuff I've been used to. But yeah, so right now I'm at basic like standard deviation stuff. That's like very basic like statistics or whatever. I've never taken a statistics class, so some of this is a little bit new to me. I had even to look up what a median was again. That's a little embarrassing, but yeah, I'm pretty beat. I got that feeling behind my eyes right now, so I think I'm going to take a little break. Okay, so I just read the third book of the Wheel of Time, The Dragon Reborn, for about 45 minutes. I still feel a little bit tired. I still got that feeling behind my eyes. And I'm not sure how long this session is going to last. And this is really mind-boggling to me, because at least last semester, when I was still at community college, I could like study for like 8-10 hours and be all right. But maybe that's because like I was studying outside a lecture. I mean, like kind of like this is my lecture, reading this textbook. So yeah, I don't know. I still do feel really tired. I'm actually even considering like taking a nap. I don't think I'm too tired. I don't think I'm tired enough to take a nap though. So I don't know, kind of in this weird limbo.
Okay, moving on to more definitions here. If we wanted to find the probability that an individual chosen at random lying between x and x plus dx, it's going to be equal to p of x times dx. I think the textbook actually uses rho, but we're just going to use p of x. And the probability density is defined as the integral from a to b of px times dx. Some more important stuff right here, pretty straightforward. And then another definition for sigma squared, or what is it called? It's not the standard deviation, the variance. There you go.
Okay, so it seems like we finished up the lesson. There's a couple of example problems that I'm not looking forward to do because I'm still pretty exhausted. I'm going to eat some lunch after this, and then I might call it a day. I mean, if I do finish this, then, then I succeeded my goal of what I said in the beginning of the video. Because I'm also trying to self-study Fourier analysis as well. So perhaps I should eat some lunch after this, then go study Fourier analysis. Not exactly sure though, because physics can be so rewarding. It's just like you gotta trudge through like the boring stuff to get to the cool stuff. it's not really cool learning about standard deviation, going to be completely honest. But I know, the stuff I'm eventually going to get through in this textbook is going to be very rewarding and very cool. So yeah, that's just part of the grind, I suppose. So yeah, but I think I'm gonna go to Fourier analysis, and I'll also do a video on that as well.
Yeah, so on to the example problems, I actually got like super cooked. I think I was just really exhausted. I'm recording this much later in the day now, and I'm not even going to go through all of my mistakes and the way I was going about things, just making things like crazy complicated. I'm actually going to come back to this tomorrow and explain more of what I'm doing and what is the correct solution and how I think about it and whatnot. So, yeah, I didn't end up finishing the example, even though I spent like an hour and 30 minutes on it. So, yeah, definitely we'll come back to it in the next episode.
And I'm very irritated. I am so angry. Um, all the introductory physics courses I've taken is, they're introductory, they're easy. So, like, you're given all these formulas and, like, it's low-key just plug and chug. There's not too much thought into it. I'm noticing a big difference here. You kind of got to start thinking out the box here. And for people that have already taken quantum mechanics watching this video, I know this problem is probably easy as heck. But I've never had to think about something this way yet in physics, So, learning a lot, it's very logical. Like, as soon as, like, I read it and, like, I understand it, I'm like, duh, how could it be any other way? So I really hope I start to build that intuition to, like, independently mathematically describe things and, like, use, like, really powerful logic. But yeah, very angry. Yeah, I'm kind of losing that ability to think. I think, like, working past this is just not going to be fruitful. I'll just keep obsessing over it, you know what I'm saying? Yeah, so I think I'm going to put it down for the night. So I was pretty close to achieving my goal. I feel like when I come back to these examples tomorrow, I'm going to be like, yeah, like, that was obvious, I hate that feeling. But right now, I definitely feel really stupid. That's pretty normal in physics. I'm still motivated as heck, though. Even though I know this is, like, really, really easy. It's not even, like, quantum mechanics. It's, like, stats. Yeah, I don't feel unmotivated. I still feel ready to go, but I feel like I need to put it down right now. And it's always hard for me to put something down when I'm not getting it. Like, I will do a problem for hours. When I first went back to school, I'm a non-traditional student, if you can't tell. When I first went back to school, it's just, I get so obsessed with problems I can't solve. And, like, I want to solve it. I do. I will literally spend, like, 2-3 hours doing the same thing. And that's, like, Einstein's definition of insanity. When in reality, it's like, okay, you need to take a break, come back to it a day later, it's going to come to you, like, so much faster. And at first I thought that was, like, an admirable trait, being able to stay locked in on a problem. You can be, quote unquote, like a superpower of OCD. That's my obsessiveness coming out. And the more I grow up, I've had OCD my entire life, since I was a little kid. And people like to say certain mental illnesses give you, like, superpowers. The more I grow up, the more I realize that they are disabilities. They're not a superpower in any way. And I don't mean to seem like all poor me about it, but I think when people just say that it's like these mental illnesses are superpowers, I don't think they really realize what they're saying. I mean, like, especially with OCD, it's like, okay, you got that obsessiveness. That's really good, right? Like, okay, like, maybe in a situation where I am, I don't know, doing my own research, I hope to get my PhD eventually, and there's going to be problems that are supposed to be, like, really, really hard and take that level of obsessiveness to actually find the solution to whatever problem you're solving. But You know what? I just don't buy that. I think that the neurotypical person, they take these reasonable breaks, and that's ultimately more fruitful. Same thing with ADHD. They're like, oh, well, you can hyper focus. Well, like my dog. Neurotypicals can just focus, like, well, I'm not neurotypical, so I'm assuming, like, most of the time whenever you want to. So, like, that, like, one segment of hyper focus is not going to beat the neurotypicals. Like, I can kind of focus whenever I want. These mental illnesses are disabilities. They hold me back. I wanted to say you all, but I guess I'm just speaking for myself. They definitely hold me back. I don't think OCD and ADHD are like superpowers in literally any way. So, yeah. Um, yeah, I think I'm gonna get into some Fourier analysis. I think I might take another break. I for sure gotta eat. Um, if I feel like I might come back to it later tonight, just because I love doing this stuff, but we'll see. I'll film it, of course, if I do. But yeah, that's it for now. I want to do this every day. Of course, the holidays are around the corner, so most likely not. But yeah, I want to. I want to be really consistent with this. I want this stuff to fill my brain constantly, and just be the things that I think about all the time.